Chavez, and today I'm going to be presenting on the effects of sleep deprivation on the brain. I'm going to give a quick outline of what I'm going to talk about today. First, I'm going to explain which parts of the brain are affected by sleep deprivation. Then, I'm going to talk about previous research on this topic. So, to begin, here we have a quick overview of all the parts of the brain that are affected by sleep deprivation, but today I'm only going to focus on two. The temporal lobe of the cerebral cortex is associated with the the process of language. During verbal language tests on subjects who are fully rested, functional MRI scans show that this area of the brain is very active. However, in sleep-deprived subjects, there is no activity within this region. The effects of this inactivity can be observed by the slurred speech in subjects who have gone for prolonged periods with no sleep. According to Chris Hembeck, PhD, 2010, the frontal lobe is one of the most fascinating sections of the brain with relation to sleep deprivation. Its functions are associated with speech as well as novel and creative thinking. Sleep-deprived test subjects have difficulties with creativity. Instead, they tend to choose repetitive words. Also, a sleep-deprived individual is less able to deliver a statement well. The subject may show signs of slurred speech, stuttering, speaking in monotone voice, or speaking at a slow pace than usual. Now, I'll be talking about the previous research on this topic. So, the first researcher, Giulio Taranti, MD and PhD, 2008, and his group have used a molecular approach to investigate what happens during sleep. They have screened more than 15,000 genes to identify all those who express changes during sleep compared to waking, and also after sleep deprivation. Taranti and his colleagues set up an experiment to identify gene expression changes related to sleep and wakefulness per se, as opposed to simply day and night. To do so, they placed electrodes on the skull of rats, who are nocturnal animals, to detect their sleep and assign them to three groups. Rats who were allowed to sleep spontaneously were sacrificed at 6 p.m. during their usual sleep period. Sleep-deprived rats were killed at the same circadian time after having been kept awake by playing with them for 8 hours. Spontaneously awake rats were killed at 6 a.m. during their usual waking period. The investigators found that while 10% of genes expressed in the cerebral cortex do change in their levels of expression during day and night, about half of them do not because of the circadian time, but because of wakefulness and sleep, regardless of time of day. This suggests that sleep may serve some cellular function, even when it has not been observed electrophysiologically. Investigators have found specific categories of genes that are selectively expressed in the sleep and in the wake brain. The genes associated with wakefulness include mitochondrial genes involved in energy metabolism, those involved in acquiring new memories, and stress response genes. Sleep-related genes are also found to be involved in consolidation of memory. In another line of work, Daniel Press, MD, 2007, and his colleagues at Beth Israel Medical Center in Boston sought to determine the effects of chronic sleep restrictions on cognitive function, in particular on working memory. Working memory is the maintenance of information in a short-term buffer for later manipulation to guide behavior. The investigators studied the working memory capacities of individuals who were restricted to 4 hours of sleep per night for 9 nights. 7 of the 12 participants in the sleep study slept 4 hours each night. 5 slept 8 hours. Every morning, participants completed a computer task to measure how quickly they could access a list of numbers that they had been asked to memorize. The list could be 1, 3, or 5 items long. Then participants were presented with a series of single digits and asked to answer yes or no to indicate whether each digit was one they had memorized. The speed of their response was measured. The longer it took an individual to respond, the less efficient their working memory. As it has been shown previously, it took longer for participants to respond when they had to keep 5 items in working memory than when they had to keep 1. Individuals who slept 8 hours a night steadily increased their working memory efficiency on this task. but participants who slept only 4 hours a night failed to show any improvement in the memory efficiency. A surprising finding by Elena Hairston, PhD, 2005, from Craig Heller and Rob Group at Stanford University, is that sleep-deprived rats actually performed better in a task that required localization of an easily detectable cue than did non-sleep deprived rats. By contrast, sleep deprived impaired performance of rats in a task requiring spatial navigation. The studies of sleep in rodents have looked at the effects of sleep deprivation during REM sleep. Dominant in the EEG of REM sleep are the theta rhythms, a specific frequency that is associated with learning and believed to be generated in the circular of the hippocampus, a brain region involved in spatial learning.